Thank you all for being here. Of course, we're here. This is the end of Elias' his master's degree. This is the defense format, of course, will be the standard. Then Elias will talk, explain his research. Then afterwards, we'll open this up for questions to general attendees rather than committee members. And then afterwards, the committee members, or Glenn Rice, myself, and Christos Gastricios, we will meet and talk about Elias's thesis and positives and negatives, and which I'm sure there will be no negative. Just so you know, Christos is online rather than being here because he was due to have oral surgery yesterday, and his jaw would have been swollen. Instead, he came down with COVID, so he's not here because he has COVID. So if you're wondering about that, that's what's going on. So with that, I will turn it over to Elias to explain his thesis.
Thank you, Kim, for the introduction. Good morning, everyone. Thank you all for coming, and to everyone online, thank you for making time out. So today, I'll be talking about filling the bathymetric gaps toward quantifying and characterizing uncertainty in interpolated bathymetry. This is going to be the outline of this presentation. We'll look at briefly backgrounds, the motivation for this research, and some of the research goals, methods, results, conclusion, and the contribution of this work. The oceans are truly our planet's last great unknown. Despite the fact that there are currently efforts going on to completely map the seabed by 2030, which I think is an ambitious goal, there is still about 75% of the world's ocean and 50% of the United States waters unmapped to modern standards. As a result of this, interpolation is typically required among sparse bathymetric data sets to fill in the gaps and create a continuous model of the seafloor for numerous scientific and commercial applications. The National Bathymetric Source Team is also creating such a bathymetric model for the United States from different sources using different data sets. And like you can see, so from different sources just like this, with different data sets that are not complete to make a complete coverage, a continuous model of the seafloor. And this project is actually aimed at creating the next generation of nautical charts, while also providing support for modeling, science, and public curiosity. Some examples of data sets for creating digital bathymetric models based on coverage. We can have complete bathymetric data sets from instruments such as multi-beam echo sounder or single beam echo sounder. And we can also have incomplete bathymetric data sets, which can be from set line spacing data sets, which can also be from multi-beam echo sounder or single beam echo sounder or skunk striping, which is actually a combination of multi-beam echo sounder or single beam echo sounder with side scan sonar. So that's combining multi-beam or single beam with side scan sonar. And another example of incomplete bathymetric data sets can be from historic or archived data sets. And also that can be from lead lines, wire lines, and old multi-beam echo sounder. So this incomplete bathymetric data set requires interpolation to fill the gaps. And interpolation actually introduces an inherent uncertainty in these bathymetric models. And as with any scientific measurement, the uncertainty that comes with bathymetry is important, particularly for safety of navigation and other modeling purposes. So because of that, I like to look at this from the from the concept of the Greenaway tool of hydrography. How deep is it? How well do we know it in terms of uncertainty, coverage, and features? And who provided the data? So who do we blame when something goes wrong? We hope nothing goes wrong. So looking at this tool of hydrography, if the quality of bathymetry and source is missing, what happens to the stool? It tilts, which is not obviously not what we want. So, in essence, bathymetry must carry appropriate and accurate quality metrics. And an important point to mention at this point is that this work only address the uncertainty part of the quality metrics. So here, so it's only not looking at coverage and feature detection. Now, the question is, who even cares about quality metrics and why is it important? We all know that bathymetry is the foundational data for numerous scientific applications. Mariners, of course, they do care because for safety of navigation, which we all know, and to avoid maritime accidents. Environmental scientists and regulators also care because they use accurate bathymetric data to study benthic habitats and to determine where marine organisms, where they feed, breathe, and live. Coastal engineers and planners also care about quality metrics because they need accurate bathymetry to build, in order to build a resilient coast. Accurate bathymetry is needed. Government agencies like NOAA also care because they use quality metrics to assess areas where new data should be acquired, and they also in compiling the national bathymetry. Insurance companies, of course, they also care. Hydrographic survey planners too care because they want to survey. They want survey to be efficient. So, like you trying to use little time and minimum resources to meet the requirement of the survey. So they also care about quality metrics and etc. So why methods for quantifying the uncertainty in depth measurements are well researched. Interpolation, like I mentioned, introduces depth uncertainties in digital bathymetric models, which have not been extensively characterized. And this is really the motivation of this work. So the main research goals are to quantify and importantly characterize uncertainty in interpolated bathymetry, arising from sparse bathymetric data sets and set line spacing survey data sets. And the approach that's been taken in this work is to simulate sparse bathymetric data set scenarios and set line spacing survey scenarios. So I would like to first look at the random sampling scenarios for sparse bathymetry. And the questions that are associated with this are which deterministic interpolation methods use the lowest interpolation uncertainties on different morphologies in an operational setting. How efficiently can the relationship between interpolation uncertainty and ancillary parameters, distance to the nearest measurement, seabed slope, and roughness be leveraged for uncertainty quantification using linear regression and some machine learning techniques? And finally, how well can these uncertainties be characterized to determine the most important predictor and understand the impact of seafloor morphology, data paucity, and spatial scales? The main idea of this methodology is to take a complete coverage multi-beam echo-surrounded data and randomly sample it to simulate sparse bathymetry, just like I said. And the first step in this workflow is to select the test and training data set based on some sampling densities, which I will get to in a moment. Then to interpolate the training data set and calculate the interpolation uncertainty by comparing the interpolation data set and the test data set. And the third step is to generate the ancillary parameters, which are distance to the nearest measurement, slope, and roughness. And the fourth step is to model the relationship between these ancillary parameters and interpolation uncertainty in order to estimate the uncertainty. And the final step is to evaluate the model. And these steps are repeated, for a number of times in order to capture the bathymetric variability due to the randomness in this approach. Because this workflow is actually the art of this work, so I would like to take some time to define the key terms in the workflow so that we can all follow me along. Now, we start with the original data, which is actually the complete coverage multi-beam data set that is based on different morphologies. Now, that will take me to the testbed morphologies that I actually considered in this work. The first testbed, which is testbed 1, is a flat seabed, which is neither slopy nor rough. And this testbed has been selected not just arbitrarily. It's visually, we can see that it is pretty flat. And we also looked at it quantitatively. And looking at the slope and roughness values on this histogram, we can see that it's pretty small and just indicative that this is flat seabed. And as we go along, we'll see the differences between the testbeds on the histograms. Testbed 2 is not slopy, but rough. And that is also this picture here, this image here is indicative of that. And we start to see the slope and roughness values picking up. Testbed 3 is slopy and not rough, and we can also see that in these figures here. Testbed 4 is slopy and rough. Also, we can see testbed 5, it's still slopy and rough, but it's unique in the sense that it was used to investigate the impact of spatial resolutions on quantifying uncertainty. So what this means is that it provides us with 3 data resolutions, which I'll get to in a moment. So now let's look at where these test beds rather are located. The testbed 1 is located in the Gulf of Mexico, and it ranges between a depth of 25 meters and 52 meters. Testbed 2 is located in the Florida Main Channel, and it also ranges between a depth of 18 to 28 meters. Testbed 3 is located in Massachusetts Bay, and it ranges between a depth of 60 meters to 200 meters. Testbed 4 is located in the Gulf of Maine, and it ranges between a depth of 12 meters and 100 meters. Testbed 5 is also located in the Gulf of Maine, and it ranges between a depth of 10 meters to 50 meters. And looking at all these data sets, we can see that testbed 1 to 4 are 8 meter resolution, while testbed 5 gives us 4 meters resolution, 8 meters and 60 meters resolution. Now, going back to the definition of key terms in the workflow, the next item to look at is the sampling density. Like I said, the sampling densities were used to randomly split the original data set into test data set and training data set. And the sampling densities are 50%, 25%, 10%, 5%, and 1%. Now, the next step is looking at the interpolation methods that we actually use in this work. Deterministic interpolation methods were used because they align well with the goal of this research, which is to generate data-driven products from large national data sets in operational settings. And these the common deterministic interpolation methods that were investigated are linear interpolation, spline, and inverse distance weighted. Now, I want to kind of define the ancillary parameters, what they mean, how they were calculated in this work. Slope, which is the first parameter, is the rate of change of depth within an analysis window. And it is calculated as a function of gradient in the X direction and in the Y direction. I should say that there are different methods of calculating slope. In this work, the method I use is the ONS method, which is given by this formula. Now, let's move on to roughness, which is the variability in depth within the analysis window. And it is calculated using the Wilson et al. 2007 formula by subtracting the minimum depth from the maximum depth in an analysis window. Now, because of the fact that terrain characteristics such as slope and roughness vary with scale, That is, their computations would depend on the resolution of the data set and the window sizes that are used for the computation. So I implemented 3 window sizes, 3 pixels by 3 pixels, which is the common window size, like window size in most standard GIS software. And I also implemented 5 pixel by 5 pixel, 7 pixel by 7 pixel. And these pixels, these window sizes rather, they were used to investigate the impact of window sizes on estimating interpolation uncertainty. Now, the final parameter, which is distance to the nearest measurement, is the Euclidean distance of the test data from the training data. Now, back to the workflow, and the next item to look at now is the machine learning techniques and statistical methods that were used to model the relationship between interpolation uncertainty and the ancillary parameters. We'll first look at linear regression, which was actually used for modeling the relationship between interpolation uncertainty and individual ancillary parameters. So, like interpolation uncertainty and distance, interpolation uncertainty and roughness, interpolation uncertainty and slope. And afterwards, I used artificial neural nets to try to capture the complex relationship between interpolation uncertainty and the combined parameters. And this complex relationship I'm talking about are like non-linearities, interactions, and hidden relationships. And artificial neural nets is a computational model inspired by the human brain's neural structure. It comprises of an input layer, one or more hidden layers, and an output layer. So in this work, the 3 predictors are the input layer, and there is 5 nodes in the hidden layer. And what each node in the hidden layer uses statistical model, like usually called activation function, to model the relationship between the input layers and the output layer. And at the end of the day, the result of each statistical model in the hidden layer are combined in the output layer to estimate uncertainty. Now, like we'll move to random forest, and this was particularly used to understand the contribution of each parameter in estimating uncertainty. And random forest is an ensemble learning method that builds multiple decision trees to make predictions and provide feature importance. Now we'll look at how the interpolation methods and the statistical models were evaluated. So what are the metrics that were used to evaluate the performance of the interpolation methods and the statistical model? So we'll first look at the interpolation methods. The first metric is distributive statistics, such as mean, like we know the median, max, maximum, maximum. And this was done using comparative box plot, because this helps to kind of summarize the distributive statistics graphically, which we all like. And then root mean squared error, which this gives the average magnitude of interpolation uncertainty. So by comparing the root mean squared error of each interpolation method. And next is paired t-test, and this was used to check whether the paired interpolation uncertainty difference is statistically significant. So what I mean by this is that whether the differences seen in the interpolation methods are statistically significant. And we'll get to see all of this in the results. Then the metrics that were used to evaluate the statistical models are adjusted R-squared, which we all know as a coefficient of determination. It measures the variability explained by the model. Root mean squared error, that also measures the performance of the predictive model. And finally, bootstrap technique. This was actually used in combination with random forest to determine statistical differences among the ancillary parameters importance. And now, so quickly, I just want to show an example of how the methodology, how the workflow that have been, that I went through, how it actually works. So this is an example of this is template for rough and slopey and original data. This is when it has been subsampled using 50% sample density. This is when it has been interpolated using linear interpolation, for example. And so now that we've gotten to this stage, we are good to we are set to extract the ancillary parameters that will be used to estimate interpolation uncertainty. And the first one is distance to the nearest measurement as slope and roughness, and this will be the parameters to estimate interpolation uncertainty. Now, I would like to look at some of the results. The results are focused on testbed 1 and testbed 4, for ease of presentation and not to bore everyone. And again, they are both on the spectrum, on the end of the spectrum. So what I mean is flat to rough and slopey. So we have slopey and rough in between. So we can actually see what is going on by seeing the two. So now, so the first thing to note is this is the box plot that I was talking about, and what this was used for. What this was used for is to compare the performance of the interpolation methods at each sampling density. So, for example, at 1% sampling density, this is how the 3 interpolation methods performed. And an important thing to note is the scale, the y-axis, has been standardized for easy comparison. And another important thing to note here is that the magnitude of the interpolation uncertainty, they are on the order of centimeters because of the flat nature of this seabed. And again, when we look at each sampling density, we will see that the interpolation methods perform relatively the same. But looking more closely, using root mean squared error values, linear interpolation slightly performs better than the 2 other methods. Now let's look at testbed 4, comparing the interpolation methods. And here, the first thing to note is that the interpolation, the magnitude of the error is in the order of meters, much more bigger than testbed 1. And again, we see the same trend. At each sampling density, the interpolation methods perform relatively the same. But looking more closely, spline performed better than IDW and linear interpolation on testbed 4. But these differences that we are seeing, are they statistically significant? So, and I answered that with the paired t-test that I was talking about earlier. And what the results show that the differences that we are seeing, they are not statistically significant. So it's meaning that the interpolation methods would perform relatively the same. Here, because it is important to understand the spatial pattern of uncertainty, what are interpolation uncertainties, what are they correlated to, and that is what this plot is doing. So looking at the left-hand side, so 1%, 10%, and 50%. And the first thing that jumps out at you is that as interpolation, as the sampling density increases, the interpolation uncertainty decreases, which makes sense. It's what is expected, which is nice. But again, looking at 1% sampling density, we'll see that where the reds, red is usually bad, where we can see the reds are really where the interpolation uncertainty values are high. And when we look at the original testbed itself, we can also see that is really where the roughness and slope values are also high. So meaning that they are correlated. So when it is rough and slopey, then we expect that the interpolation uncertainty is high, which is what is expected. On testbed 1, there is an interesting observation here, because most of all the interpolation uncertainties are concentrated on the eastern part of the plot. And why is this? This is actually because of multiple artifacts on the original data set that was used. So meaning the quality of data set that was used for interpolation also affects the quality, or also affects the interpolation, also affects increases the interpolation uncertainty values. Now, this is the result of the relationship between each parameter and interpolation uncertainty. Looking at the left plot, like A, B, and C is the adjusted R squared, which shows the relationship between distance and interpolation uncertainty. And what we see here is that the relationships are weak between interpolation uncertainty and the ancillary parameters. And looking at the right plot here, like this, that's the Whitman squared error, which is actually the error in the prediction. And as the sampling density increases, interpolation or uncertainty decreases, which makes sense, and that's what is expected. Now, what happens when we combine the interpolation of the ancillary parameters together to estimate interpolation uncertainty? And what we'll see is that, yes, like artificial neural nets, improve the model, but in a very marginal way. So yeah, it performs better than when we are looking at each parameter individually, but it's still not as strong as we would like. Now, on this plot, I want to show the importance of parameters on each test bed. So how does each parameter contribute to estimating interpolation uncertainty? And what we'll see here is that roughness dominates. Roughness is the most important predictor on the test beds. On the right-hand side, which is the performance of interpolation models on the test bed. So how does the predictive models perform on each test bed? And we can see that test bed 4 performed better than the other test beds. So test bed 4 followed by test bed 3, 2, and 1. So because of the fact that test bed 4 performed better than the other test beds, so that's why it was chosen to investigate the impact of window sizes on interpolation uncertainty. And what we can see is that at 1%, 5%, and 10%, let's concentrate on A, which is IDW, because the trend is the same across through the interpolation method. So what we see is that the 3x3 window size performs the least at those sampling densities. So at 1%, 5%, and 10%, it performs the least. But getting to 25% and 50%, it performs better than the two other window sizes, that is 5x5 and 7x5. And what this means is that, yes, window sizes impact estimating interpolation uncertainty, but it is not directly related to smaller window sizes that we expect to give us higher prediction ability, but that's not the case here. It is actually dependent on the sampling density that is used. Here is the result of the interpolation uncertainty, the result of the impact of data resolution on interpolation uncertainty, and this was focused on test bed 5 that gave us that 4 meters resolution, 8 meters resolution, and 16 meters resolution. And what we can see is that higher resolution is the best. So in this case, with higher resolution, we can predict interpolation uncertainty. So as we can see in all the results, and looking at the errors to the higher resolution, the errors in the higher resolution data are smaller compared to the lower resolutions, which is good, and that's what is also expected. So I would like to kind of put all these findings together, and that would be the way I've done this is to like, okay, what the questions we wanted to answer, let's see how we've performed. So the first one is, which deterministic interpolation method gives the lowest uncertainty on different morphologies in an operational setting? Linear interpolation performed the best for testbed 1, while spline performed the best for testbeds 2, 3, and 4. However, the absence of particularly significant differences indicates operational equivalence of examined interpolation methods. How efficiently can the relationship between interpolation uncertainty and auxiliary parameters be leveraged for uncertainty quantification using linear regression and machine learning techniques? We can see that the relationship between individual parameters and uncertainty are weak, although they were statistically significant. The machine learning technique that was used, artificial neural nets, improved uncertainty estimation, but marginally. And this kind of tells us that this problem is a complex one, and it also indicates that there are some factors driving uncertainty that were not accounted for, or probably there is a strong random component within interpolation uncertainty. So how well can these uncertainties be characterized to determine the most important predictor and understand the impact of seafloor morphology, data paucity, and spatial scales? Roughness is the most important predictor of uncertainty, and distance is the least. Interpolations are best performed on less complex morphologies like testbed 1 and testbed 2, as we saw, like with the magnitude of interpolation uncertainty. Interpolation uncertainties have non-random spatial components across testbeds, so they are driven by like some factors like by some factors like the complexity of the seabed. Uncertainty estimation performance varies across the testbeds. Spatial scales, that is like data resolution and window sizes, impact uncertainty estimation. Why higher resolution, higher data resolution enhances uncertainty estimation. Optimal window size depends on sampling density. And now take me to the other part of the work, which is the set line spacing survey scenarios. The questions are similar, but the one that is really different is the third question, which is how well can these uncertainties can be characterized to determine the most important predictor and understand variables that drive set line spacing density. So that's really the major difference between set line spacing scenario and the random sampling scenario. The same, almost the same workflow was used, but the important difference here is that instead of using sampling density, some selected line spacings were used, and we'll look at that now. The main scheme spacings, like usually called main line spacing in all parts of the world, but in the US it's called main scheme. 60 meters, 32 meters, 64 meters, 128 meters, 256 meters, and 512 meters. And this is just an example of the 256 meters. And coastline spacings have been calculated using the know-how specification of 9% of the main mileage. And this line density, these line spacings have been chosen to really understand how how we can predict interpolation uncertainty at relatively tight line spacing and wider line spacings. So I'll just show some of the results, like focusing on testbed 4 and looking at all the line spacings from 16, 32, 64, 128, 256, and 512. Firstly, is that on testbed 4.2 here, the interpolation uncertainty, the magnitude is in the order of meters, but at the lower line spacings, like 16 meters, 32 meters, and 64 meters, we see that the interpolation methods, the performance are relatively like the same, but coming to higher line spacings like 128, 256, and 512, we can see like the differences now is now picking up. I should also mention here that the differences that we are also seeing here, they were also checked and they were not statistically significant. Now, to look at this, the special pattern of uncertainty on this test bed using the line spacings of 32 meters, 128 meters, and 512 meters. And what we can see again is that lower line spacing, like decreases interpolation uncertainty, and as we move along, like it increases. And again, here the interpolation uncertainties are actually correlated with the same thing that we saw in the random sampling approach, where the test beds are really rough and slopey. The interpolation uncertainties are also high there. And this is the modeling result, like showing the relationship between interpolation uncertainty and the estimated uncertainty using distance, roughness, and slope. And again, the relationships are also weak. The relationships are also weak, and with as the line spacing increases, here, the magnitude of the error also increases. Now, combining all the parameters like distance, slope, and roughness, like using artificial neural nets, we can also see that yes, it's improved, but it's just marginally not as good as we wanted. Now, the importance of parameters on the test beds. Here, there is an interesting thing going on. On test bed 1 and 2, on test bed 1 and 2, slope was the most important predictor of uncertainty. And moving on, like to test bed 3 and 4, we can see that roughness is the most important predictor of uncertainty. And looking at the performances of the uncertainty models on each test bed 3 like performed better than 4, and they're followed by test bed 3 performed the best, followed by 4, 2, and 1. So again, the key findings in this approach is similar to the random sampling approach, because like the linear interpolation also performed the best for test bed 1, while spline performed better like for test bed 2, 3, and 1, like based on root mean squared error. But like testing if there were any statistically significant differences, we saw that there were no statistically significant differences in the performances of these interpolation methods. And the question of how efficiently can the relationship between interpolation uncertainty and ancillary parameters be leveraged for uncertainty quantification using linear regression and machine learning techniques? We also saw that it's here too. It's the relationships are weak, although they are statistically significant. Machine learning also, the artificial neural nets also improved uncertainty estimation, but marginally, also showing that there are some factors that are driving uncertainty that are not being accounted for, or it's just really random. Like there's a strong random component within interpolation uncertainty. Then the question of how well can these uncertainties be characterized to determine the most important predictor and understand variables that drive set line spacing density. Roughness and slope competes here as the most important predictor. Distance was seen to be the least important predictor. Interpolations are best performed on less complex morphologies like testbed 1 and 2, especially for set line spacing survey. But of course, like, does that mean that set line spacing survey cannot be used like in rough areas? Yeah, it can be used, but it means that the line spacings have to just be denser. Then interpolation uncertainty here to like have random, non-random spatial patterns across the test beds, and the performance of interpolation uncertainty varies significantly across the test beds. And the impact of line spacings on the model's predictive power was also evident. Now, I want to try to put everything together by looking at what are the contributions of this work. The first one is seeing the operational equivalence of the examined deterministic interpolation methods. And again, that the fact that data quality, sampling density, line spacing, and spatial scale impact uncertainty, slope, roughness, and distance to linear measurements, which are the auxiliary parameters, are important predictors of uncertainty, but they cannot just do this alone. Set line spacing solving designs are best used on simpler morphologies, like I mentioned earlier. And seabed morphology should drive set line spacing density. So if we are on a complex seabed morphology, then like the line spacing have to be tighter. And again, although while this work, we saw that the relationship between the combined parameters and interpolation uncertainties like were weak, but it lays a foundational understanding for estimating interpolation uncertainty and also characterizing it in bathymetric model, which is a good step. And with that, I would like to acknowledge a lot of people. Like I won't dare to mention names, but like everyone that is here, thank you. Like everyone that's come to this presentation, thank you for all the support. Like I would like to thank my committee members. They've been so supportive and wonderful. Thank you for all the teachings. The CCOM faculty, like all the professors, they've been so great. The IT team, admin staff, Colin, everyone, like thank you so much. The MBS team, Glenn and Katrina, thank you. Kizlang actually helped with, of the Department of Math and Statistics, helped with some statistical insights, like doing this work. So I would like to also acknowledge him. All my CCOM friends, the GEPCO scholars of the years 18, 19, and 20. Yeah, the summer hydro team of 2022, ocean exploration tours. And I also like to thank MTS, Marine Tech Society, Society of Underwater Technology, and the Society of the Hydrographic Society of America for some scholarships that were awarded to me. The UNHYSS team, my Nigerian family in the US, friends and family, and my genuine wife. Thank you, everyone. And I can take questions now.
Do we have questions?
So when I think of lens spacing, I think about just coverage, right? So you want more swath coverage on your outer groups. Why do you think it's when you get so many data points, anyways, with mapped? Why do you think that it's actually impacting your uncertainty so much?
Sorry, I'm
just curious why you think line spacing is having such an impact on the uncertainty.
Yes, because it depends on the coverage that you have on the seabed, right? So, and again, the places where set line spaces are really used are shallow waters. So, and on shallow waters, like your swath is going to be very small. So, it's in fact sometimes you don't get any advantage of using multi-beam. Instead of using multi-beam, most people what they do in the field is even to use single beam echo sounder, because they don't gain so much from using multi-beam echo sounder because the water is so shallow. So that way, because of that coverage that you have, you still have gaps on the seabed. So which means you have to interpolate, and that's really what drives the uncertainty.
So it is the data density.
Yeah, it's the data density. Yeah.
I have a couple of questions. Oh, is it me?
Yeah.
Yeah, cool. I have a couple questions. First of all, I thought it was a wonderful presentation. And I think that it's a really unique idea, or insightful, I'll say, to take a perfect scenario and break it up into a test and training set, because we know how difficult it is to get validation data. But I'm curious, what is the architecture that you chose to use for your neural network? Like, did you go the convolutional route, or?
Yeah, so it's not convoluted, it's artificial neural net, and just like the architecture that I showed there, it's just you have the input layers, right, which are the parameters that are used, and I had like the hidden layers which had 5 nodes, and so it's kind of forward propagation, like if that's what I know, like computer science, I like students, so like probably know better than I do, but so it's forward propagation, and okay, yeah, so let me look at in those hidden layers, the statistical model that was used was rectified linear units. So that was what was used to find the relationship like between the input layers and the output layers, right? So like that was really what I did. So I'm not sure if I answered your question.
You did. I do have a second part to the question, okay. A little slightly unrelated, but because you use a ideal scenario to kind of break it up into something that you can then create a measure of uncertainty, have you considered, or do you plan to at some point try this technique on a non-perfect data set, a data set that doesn't necessarily have a sparse data set, one that doesn't have complete coverage? Does that make sense?
Yeah, so but I mean, you don't know whether you've interpreted the data is right or not, because you don't really know the true the reality of what's going on there, right?
Fair enough. But you have an idea of the different types of seabeds that give you, or the different
So at the end of the day, the goal of this work is that once we have good predictive models that are working, then we can use that, we can apply that to areas where we interpret data. So I think I get your question now. Yes, exactly. So we build this predictive model. Once we are good, and like the results are they are good, at least we don't necessarily have to have 100%, but 80%, 75% of like that confidence is good, because the ideal thing is you should go out to the field to collect data. That's really the ideal, but because of course, we know how expensive it is to go out there. So we need to do something, right? So once we have predictive models that we feel that this is working good enough, then we can use that in other areas where this is not done, where we have just fast data.
Thank you.
Yeah.
Other questions? Fine.
Are you there again?
Hmm?
Do you have a model?
No, I'm not there yet.
I'm not there yet. So follow-up question happens next. What needs to happen to get you there?
Yeah, so I mean, couple of things. The first one is like to probably change the approach. I kind of use the spectral analysis approach. That way, instead of the way I parameterize the data set, we are not going to do that. Like kind of build try to understand the energy that is coming from the tip floor, and can try to use that to estimate what the uncertainty is going to be. So that's going to be the next step, trying the spectral analysis approach. That's going to be the next step. And if that, depending on what we see, and we can see the possibility of combining that with also with machine learning techniques. So that will have the best of both worlds. I think that will probably get us closer, but fingers crossed.
Andy, you ready?
Yeah, thank you. So, question first in your sparse, maybe a comment and then a question following the comment. So, most of the sparse data sets that exist that you want to look at in the historical record are except for those maybe before 1920 or something, are not really randomly sparse. They're systematic surveys which are subsampled along a specific set of lines. And so you treated your test as random samples. And so do you think that the fact that the sparse data sets are not totally random would affect your outcome?
Yes, I think so. It's going to definitely affect me. So which is why it's also interesting, aside from even just sampling randomly, we can also do that, sampling based on set line spacing, but it's not just going to be continuous. So like you kind of simulate what you have, like that systematic approach. Yeah, that is also something to consider. Yeah, but that's a very good point. Yeah, and again, like Glenn has mentioned that a lot of things, like a number of times. So.
And if I may, into the set line spacing. So the International Hydrographic Office standards have, the S44 standards have a set of rules on line spacing. And so one of your aims is to identify, what should the line spacing be on set lines spacing. And so have you looked at those rules to see how those rules compare, or are they right or are they wrong?
Yeah, like so that's not something that really dig into, but I think like just from my knowledge of what S44 is, those standards are based on water depth, if I'm not mistaken. So I've not really dig into that. So and in this case it's really shallow. So I'm not sure if that is going to apply, but yeah, it's something to also investigate.
And following up on that, and this is maybe my last one.
You only got one more.
It's been an article of faith for years in single beam soundings that the orientation of lines should be essentially perpendicular to the depth contours. Have you considered the orientation of lines and set line spacing as to how it would impact the
answer is
uncertainty?
No, the answer is no. I've not looked at directionality. That's like that if directionality actually affects uncertainty. No.
You actually have, in a sense, because you've looked at the relationship with open. And in a sense, in looking at the relationship with slope, you're looking at the impact of running a line orthogonal to the contours as opposed to along the contour. That would be the flat case. That would be the, so in a small sense, you haven't looked at the bigger picture that takes a look at the overall impact.
Yeah, maybe you should stay on for a PhD to start looking at it.
The issue is the lines that you selected are not specifically oriented to. So any effect of that would be affect you to proceed.
So that actually would.
I think the answer is still.
Yeah, if you go back and do about slide 47 or something like that, and I just might be confused here. It was one with the big histogram. There you go. There you go. And so the two test cases, the flat and the rough case, which are not slopey at all. Don't say the word.
It's a roller.
Are the ones that show the biggest impact of slope, and I'm just confused by that.
Minus 3 bars.
Maybe because you can see that. So distance, slope, and roughness. So let me try to get your question. The reason why
Test bed 1 and test bed 2
yes
are not slopey. They're not sloped.
Yes.
But yet that is has the biggest impact.
Yes, that's something I also kind of struggle with, and kind of why is this going on? And what I came to was, despite the fact that we say that it's not slopey, it's not slopey, but there's still some if you look at those histograms that I showed, there's still some you can't say slopey, you can see that there are still some slopes on those things. So it's not entirely rough and slow, you still have some interactions going on in there. So I think it's really because of those interactions.
You do have a non-zero slope.
Yeah, exactly.
And then maybe the issue is not really what the slope is, but the slope relative to it's a differential change.
Exactly.
The slope and rough parameters here are basically measuring the same thing. There's going to be correlated.
Yes.
Yeah, there's no big deal.
The other thing that's going on knowing these data is on the first two test bed, roughness is almost a constant. And so when you have a constant, you're trying to predict against a constant. But there was another question over there.
Yeah, I just wanted to ask about the one result you had for this flat. You had half of the data. You said it could have been some multi.
Oh, yeah.
I was just curious. Did you look at the uncertainty? Did you assume the uncertainty of your original data was 0?
Okay, yeah. So like that's something I didn't mention. Like the test beds, like an assumption I was made in this work is, they are perfect, which we know that they are not. Like they are errorful, which we know that the original data set has some like uncertainty associated with it. But like for now, I kind of just ignore that. But the eventual goal is to be able to integrate that measurement uncertainty in the original data set into interpolation uncertainty, so that we can be able to assign capsule allocations like, oh, okay, yeah, this is A2, this is A1, this is B. Well, like, so that's why I didn't even show capsule at all in this one, because it's it won't make sense.
Yeah. Did you consider when thinking spots about either for future tests or why to include or not include a site where you have single feature in a very different from the surrounding morphology? Whether it's a flat bed and a rock sticking up, or it's a shipwreck, or it's rocky and there's a channel and everything else is the same. Did you consider what that might do to your predictions, or why are not try that yet?
Yeah. I mean, it's like one step after the other, like one step after the other. Yeah, but like, yeah, I think you have an important point. But in the end, like, it's definitely going to like increase the uncertainty. It's going to increase the uncertainty. If you have just a feature like like maybe like a leg, definitely it's going to increase the, and you won't be able to and again, maybe that's one of the reasons why like we can just explain about 50% of the variability in uncertainty in the uncertainty, because there are some things also going on in this, like on the seabed that we can't actually see, but because we are just trying to make an informed guess, so those things will still like impact us eventually. But like that's something that would like the risk aspect of it, after we even have a model that we think is working. Yeah, it's not 100%, but so that's something that that will deal with later in the future.
All right, I think we'll take just one more. There's none in here. Are there any online?
Haven't seen any.
Okay. Okay. Yeah.
So I saw that the folks at Jamstack in Japan have been playing around with machine learning and kind of do something slightly different, but along kind of similar concept of trying to infer more complex terrain from coarse grid. Have you looked at what anyone else has been doing in terms of trying to predict before roughness and patterns?
So sorry, can you come back with? I'm not sure I followed.
Folks at Jamstack have published a paper on, they've taken a coarse grid. So it's kind of similar to coarse space sampling, right?
Yeah.
And they've tried to use machine learning to create a fine resolution grid. So they're trying to like make up their own morphology based on what they know of other areas that kind of make a pretty picture of what the actual morphology would look like. Have you looked at what other folks have been trying to do in terms of that sort of predictive roughness interpolation?
No. That the answer is no.
Short one question.
Okay, short line.
Yeah, I don't think it's a good idea, because it's like you are trying to like make up the seafloor. Yeah. So personally, I might be wrong, but like of course, and it's open to like the investigation. I know the fact. Yeah, I would like to like see the paper. So I'll follow up with you later. But personally, I don't think it's a good idea, because I don't
That
have
is the right answer.
But we're gonna find out.